All right, so we're continuing on talking about open channel flow because this is one of the key things that you're interested in here as roadway planners. And this is a picture that I took in Colorado, I think in 2011. So my plug here is not specifically for Colorado, although it's a magnificent state and there's lots of cool things to do there. But embrace those opportunities to travel, whether it's for work or pleasure, and get out and see different parts of the country and other countries and do cool stuff, because I keep thinking about some of the neat things I've done, especially when I'm kind of feeling down in the dumps. Like maybe when there's a thunderstorm and it's pouring rain and I'm soaking wet, and it makes me feel good. So take those opportunities as you can to travel. Learning out objectives for this. We want to recognize various channel lining types and materials that you may use, probably in your situations more for your swales and your roadside ditches and things. We're going to talk about and list the steps for a stable channel design. And we're actually going to, I would say, walk through a stable channel design, because as we will see, and I mentioned this morning, keep your eye on the prize. The big picture concepts are the important things. The details and the minutia, honestly, I forget them all the time. I don't have that special knack that a lot of people do to remember like all of the exact equations and the parameters and the charts and the figures. However, you can always look that stuff up. You know where the references are, you pull them off your shelf, you look up the information that you need, but you need to know what you need and where to find it. That's the big picture stuff. The minutia of the equations, if you're into that, that's great. If you're not, it's not a big deal. Don't feel bad about it whatsoever. So we're going to walk through a stable channel design because depending on what type of lining you're looking at, it could be fairly straightforward or it could be a bit complex and literally in the weeds or vegetation. And that's the example that we're going to look at, one that's in the weeds. I don't know why this road is this pinkish purplish color, but it kind of looks kind of nice. It's probably the some of the settings on the camera that took the picture. Again, the resources, the Federal Highway Hydraulics website has a wealth of free stuff on it, so please, again, check that out if you haven't been on it. We will talk in this lesson about the Hydraulic Toolbox software program a bit, and I'll show you how I actually did over like 3 minutes in my lunch break a stable channel design that if you did it by hand would probably take you a couple hours to do. If you're slow like me, it might take you 2 hours. Our key reference, Hydraulic Design Series 4. So you noticed when I put up the solutions to the couple of practice problems in the last lesson, I was scrolling through pages of a PDF. The problems that we're talking about, if you want to go back and look at them, they're in Introduction to Highway Hydraulics. The solutions are printed in there with the step-by-step process. So if you have questions, just refer back to HDS4. The other document we'll be talking about that refers a lot and has the detail on channel linings is Hydraulic Engineering Circular 15, Design of Roadside Channels with Flexible Linings. I think that would be of extreme relevance to you. All right. So rivers, streams, and constructed channels. Roadside ditches and swales and things like that, maybe some biofiltration measures. You know, those are constructed channels. We designed them, we cut them in there. We gave them certain slopes and geometries and outlets for the water that's collected. So here's kind of a distinction between maybe some stuff that's common to your work and some stuff that's more common to hydraulic engineers who just basically deal with water stuff on a full-time basis. So as hydraulic engineers, we might do channel design, channel stability, stream and river channel stability projects, building our large culverts and bridges over streams and rivers, looking at scour issues. Those are things that fall within the realm of hydraulic engineers, and sometimes we even need some more specialized help. So if you get into like some stream restoration projects, which don't typically fall into the realm of state DOT work, but if they're like mitigation projects, then we may get into this stuff a lot. The people that are even more in the know on that type of thing are what we call fluvial geomorphologists, or kind of like river, you might think of them as like river scientists, might be a good way to describe them. And they do probably a bit more of like stream restoration. As hydraulic engineers, we get into stabilization projects, but as far as trying to return a system to its natural dynamics and reincorporate the natural ecosystems, you get into biology and fluvial geomorphology and maybe some other types of specialty disciplines. Now, more on the roadway design side, we're looking more in regards to open channel flow, your roadside ditches, your swales, those types of things, and then of course your smaller culverts, maybe some storm drain systems and that sort of thing. So with that, does that seem to replicate the division of responsibilities within MoDOT? You have full-time hydraulic engineers, is that correct? Is there like a unit, or is there a person in each district, or how does that work?
It's, at least in our district, I'm pretty sure it's just like whoever is basically been looking at the longest, but they're just so classified as a design engineer, but they just are a design engineer who knows a lot about drainage.
Okay.
It's not like an official title or anything.
Okay.
Yeah, I think MoDOT has bridge hydraulic engineers.
Mm-hmm. So
They're in the
hydraulics.
bridge section.
Yeah.
And
then
then
they
roadway
have-
drainage is handled more by roadway designers, and there might be a senior person as kind of like a resource person in the district. Okay, do you each of you know who that person is for the area that you work in? And if not, that might be something to figure out, right? And if you figure it out and there's not a person that you've identified, then that's probably telling in itself, right? And maybe that person becomes you. You just enjoy this class so much that you just want to do it. All right. So why ditch design? Well, think about concrete. What do we know about concrete once it's placed? What does it always do? It wears away, but before it wears away, what does it do? Concrete always cracks, period. It's a given. It's like death and taxes and whatever. Concrete cracks, water erodes. When we place concrete, when we design concrete structures, we have construction joints, contraction expansion joints. We actually dictate where the concrete is going to crack. So we manage and mitigate. Well, the same thing with flowing water. We know that it's going to erode, and it could potentially cause issues. So we manage and mitigate, and so we hopefully do a good job with our ditch designs and our swale designs and our stream and river stabilization projects, so we don't have nonsense like this occurring. Because then we just have to go back in and fix this, and then we still have to deal with the water anyway. So we need to be proactive and take care of it the best we can the first time around. So ditch design has a lot of design variables in it. Here's some of them that I've listed here. What's the design context? Is it on the cut side, the fill side? Is it in the median? Design discharge, I think we've already talked enough about design discharge. And you're probably using a return period of about what for your roadside ditches?
Depends on the what's nearby it, and depending on the level of service, like rural lettered routes will not have as high a return period as like we'll use for interstates.
It depends on the ADT.
It depends
Yes.
on
Yeah.
it depends on the traffic volumes. It depends on, so it's kind of like a risk-based decision, give or take. So for an interstate, what return period would you use for your ditch design?
25.
25 or 50? Well, it's in your
Yeah.
EPG.
Engineering policy guide.
Yeah. Okay. So, and I actually don't know. Again, it's just me being lazy. I didn't look at this stuff. And even if I did, I might not even remember it the next time. So. It's in your EPG though, so that's good information to know. I think 10 years fairly common for a lot of roads, but again, it's a risk-based decision. Once you have the flow, then again, we transform the flow into depths, velocities, and shear stresses, and then we base our design on those and more parameters. Shapes, V-notch sections are pretty common, trapezoidal sections are pretty common, maybe semicircular sections, so they're different kinds of shapes. You have to establish the slope, and we'll talk about freeboard here in the next slide, I think, or the one after that. And you really need to be sure what the material, the natural material is like, and what the lining material may be like if you need some lining material to keep that integrity of the ditch line so it doesn't erode during your design flows. All right, so here's kind of like the freeboard idea. This is probably in your EPG. You can have a certain depth of flow in your ditch line before maybe it gets up to the bottom of your subgrade, or maybe it's within a certain distance of your paved shoulder. There's usually some sort of a criterion like that each state has for their ditch design policy. Ditch slopes, it's important to maintain at least a minimum slope so that you have positive drainage and you don't have standing water in your ditch lines. Because standing water in your ditch lines, standing water above the upstream end of your culvert, along your embankment, situations like that, they can cause some long-term damage to your embankment. If you have full saturation of that embankment, it can cause some problems with your embankment and your subbase and your base course and your wearing course of your roadway. On the other side of the thing, we know that steeper slopes have higher, what's the slope a primary driver of?
Velocity.
Velocity. Think about the water part. You don't see your water slides like this, right? They're always like this because slope drives velocity. So with steeper slopes, higher velocities, higher shear stresses, we need to make sure that we know what the shear stress that's imparted on our ditch is going to be, and its maximum, and that we account for that, and that we won't have an erosion issue. And so again, here's that picture on the intro slide. Some different kinds of ditch linings. Of course, the natural vegetation always looks nice. Here's temporary lining, turf reinforcing that with some check dams, and check dams are there to slow the velocity until you can get your vegetation road established. Riprap lining, articulating concrete blocks or interlocking block mattresses. Issues with these, it comes down to one big thing is collaboration. And who are you getting the permits from, and what do they think about stuff like this? And resource agencies and permitting agencies, and Veronica could speak to this at length, they don't necessarily like the looks of riprap. I think in the past, Veronica, you probably worked on projects where they wanted the riprap buried in topsoil and planted, and that lasts probably until you have a flood come through and then it gets washed out. But aesthetically, it can be a point of contention, and probably from an ecosystem perspective, when we're looking at co-benefits and ecosystem benefits, it's probably not near as good as maybe something that incorporates a lot of natural vegetation. However, the flip side of that is riprap and mattresses and gabions and other types of things can accommodate much higher shear stresses or tractive force in natural vegetation and temporary erosion control measures. So what we get into a lot of times is compromise. Can you take something like this and still have some vegetative plantings here, maybe willows or other types of natural vegetation, and kind of do a hybrid approach? And hybrid approaches are going to compromise, but they may be easier to get permits for. We have concrete ditch linings, and honestly, I don't think as hydraulic engineers we're a fan of these. What did you think could happen with this one that you see here on the left?
Have your flow coming off of it and then ramping up.
Or you can get under it and erode it.
Yeah.
Going back to our three big equations, right? One of them was conservation and momentum, and we know that water, when it starts in a direction, it likes to continue in that direction unless you apply an external force to it and cause it to change direction and momentum, right? The water's gonna come right down out of here during your flood event, and it's gonna shoot right over this and cut this all out and gonna continue down here to whatever is in its way and cause some problems. And the other thing is these actually become kind of like concrete tunnels, right? So the water jumps out, and if these aren't done correctly, and especially on steeper slopes, it will start to cut underneath, it will go through cracks, and all of a sudden you'll have a situation where you have more water flowing underneath these things than through the actual constructed channel. Yeah, I guess I personally am not necessarily a fan of concrete line ditches. Soil cementing, I think that's used probably a lot in the southwest. In the southwest, you have these dry, arid environments. It's hard to get natural vegetation to grow. And so if you can maybe mimic some of the natural soils and get this colored the right way, doing some soil cementing or roller compacted concrete or things like that, you can still get some of the aesthetics of the natural environment even though it's not vegetated. So ditch design criteria. We talked about that at least your design flood or your design flows for your ditches is a risk-dependent thing. Has anyone else done some roadside ditches, and what did you use for design criteria? And if not, that's okay.
The last one I did was a 10-year,
10-year?
and it was a low volume highway.
Okay. Is there anything specified as far as freeboard and what that relates to, as far as water level in the ditch, how high that water can get?
Not that I remember.
Okay.
There is, but I don't remember.
There's a few things for like median.
Yeah.
So, I mean, if we need that.
Yeah. So that's a key point right there. I mean, that's the success is you know that there are different design criteria for your ditches and your swales and other things. And you can look in the EPG when you get into that and make sure that you're following the right procedures and design criteria. That's a win. Well, hydraulic analysis, it comes back to our good old friend Manning's equation, and I think we've talked about this sufficiently. This is a perfect application of Manning's equation. You can assume steady uniform flow conditions in there, and we know how to use Manning's equation. So here's some different cross shapes, cross-sectional shapes, trapezoidal, circular. Veronica may hit on this tomorrow. Here's kind of like your gutter pan, and you may see a different form of Manning's equation used for this because it comes down to some issues encountered with trying to calculate the hydraulic radius in some of these shapes with these real narrow corners. But it's still basically an application of Manning's equation, and it's just been tweaked a little bit. All right, so we talked about, and we actually did a quick calculation of hydraulic radius, and again, that's just the flow area over the wetted perimeter, or the boundary that the water at your design event is coming in contact with. And we even saw that for our trapezoidal section, it starts to get, there's a little bit of math involved and some extra calculation involved for the hydraulic radius for trapezoidal. Now think about if you had an irregular cross section, if you had something surveyed, like in a river or whatever, and it has like a low channel in it, and it's kind of funky along the sides. There's no way you could actually solve that by hand and do, there is a way you could estimate it, but it gets very, very tedious. And that's why we have hydraulic programs like the hydraulic toolbox and other types of programs that will actually do those calculations for us, and we can get away from the tedium. Roughness values. All right. So if you've designed culverts or storm drain systems, you know that there's typically a table that you look up For concrete, you might find, what's a typical value of manganese N for concrete pipe or something?
0.013 or
0.013 is pretty common. For corrugated metal pipe, you might see something starting at like 0.024. Same thing with a plastic pipe, and the deeper those corrugations get, the higher the manganese N goes. When we're dealing in open channel flow, and it was talked about this morning, we get into this thing that's called relative roughness. And where this came up was in the time of concentration in the sheet flow. When you have a flow depth that's much deeper than the roughness elements on the boundary, or the roughness depths on the boundary, it doesn't become an issue and you never hear about it. When you start to have flow depths that get down into your roughness, your grass, your cobbles and gravels and boulders and whatnot, and that water is like down in here and is trying to weave its way through there, it experiences the roughness a lot more than when it's way up here. So as an example of this, kind of like a metaphor, I grew up in rural Pennsylvania north of Pittsburgh, and we lived next to kind of like a defunct strip mine. And so, after they stopped the mining, the vegetation and stuff started to come back, and we had like acres and acres and acres to roam around. And we go, my brother and I would go on long walks with my dad. And so, this is like when we were wee little, and my dad is like a little taller than me, and as kids we were like down here, right? So we would go through and we'd be walking through like the brush and the weeds, and for my dad, the brush and the weeds were like down here, but when you're this tall, the brush and the weeds are like coming up to here. So he'd be just like chugging along, and all of a sudden he'd be way far ahead of us, and we're just kind of like getting whacked in the face with branches and weeds and everything, and we're facing a lot more resistance, right? Well, the same thing happens with water. When water's way up here, it just blows over that resistance and experiences a little bit of friction loss, but not as bad as when it's trying to snake through those weeds and it's getting whacked around and whatnot. It has a relative resistance that's much higher. So when we get into open channel flow, we always need to consider the relative roughness effect, and it's dependent on the flow depth and then the size of those roughness elements. So that's a key difference. More detailed information on this, again, is in HEC 15, but getting the basic concepts of what we're striving for here. Relative roughness. So when you hear that, you kind of know what's going on. And you're probably dealing with some open channel flow things. Flow in a river channel doesn't encounter really much relative roughness. We still choose manganese N's based on, this is kind of rocky. Go to a picture guide and say, it looks like this, and then choose a manganese N. The flow out in the floodplain is shallower, slower moving, and so it encounters more of that relative roughness effect. All right, so there are tables for this. So there are tables for vegetation, for calculating manganese N, for vegetation, for rocks and cobbles and whatnot. And so here's an example of one for riprap, cobbles, and gravel. And you can see that there are different categories here: gravel, mulch, cobbles, rock, riprap. It gives you an idea of what the D50 is for that material. When I say D50, do you know what that means? Is everybody okay with that? Okay. And then over here, you see it. You see, disregard the meters, but you see manganese N for selected flow depth. So you have half a foot, 1.6 feet. I think that's because they probably did this initially in metric, and then they made the conversion. So that's why you see these weird increments: 1.6 feet and 3.3 feet. And what do you notice? You take one of these, you see that the relative roughness decreases as the flow depth gets higher, because it's not experiencing as much energy loss. It's kind of like coasting through it much easier than when it's way down here hiding and trying to snake through it. So there are different tables again for vegetation and rock and other types of materials. When you get into vegetation, it does become more complicated. Manganese N for vegetation, again, as it says here, varies with type of vegetation that you're working with. How dense is it? How thick are the stems, and what is the stem height? Okay, and then it also depends on flow depth. So with vegetation, depending on the type of vegetation, as the flow gets deeper, that vegetation will tend to, as it experiences more stress in the water, it will tend to
Fold over.
fold over, lay down. It's kind of like people, right? When I get stressed out of work, I just want to lay down. I just want to like climb under my desk and take a nap sometimes. Don't you ever feel that way when you get stressed at work? Well, the same thing with vegetation. It's like, I can't handle all the stress. I just want to lay down. Just leave me alone. So when it lays down, what do you think happens to us? It's the roughness as it flows one over. It'll decrease. Right, exactly. Okay, same things happen. Things like that happen with vegetation all the time. As it lays down, the roughness changes, and that's usually with higher flow depths. So we need to be conscious of that, and again, that's a relative roughness. All right. So when we get into our ditches, we know how to size them for capacity using Manning's equation, right? We have our design flow. We can calculate for that design flow and the geometry and the slope of our ditch line, what the depth will be, and make sure that that meets our design criteria. We also need to know if that ditch line and that natural material is going to erode or not. So we need to check that, and we do that check on to see if there's going to be an erosional issue. And we use what's called a shear stress analysis. Actually, I think back in the day we looked more at comparing permissible and flow velocities. So we would say that this soil type or this type of rock or whatnot has a permissible velocity of 10 feet per second. And then if we do our calculation using Manning's equation and we see the flow velocity is 11 feet per second, that is the first indication to us that that material may move and start to erode. Shear stress is more of a physics-based and realistic procedure, and it gives us better results. And so Federal Highway has shifted towards looking at permissible and applied shear stresses as opposed to permissible and flow velocities. Okay? So we actually have gone towards shear stress, and I don't know what MoDOT does, but I think a lot of states use a shear stress analysis to see if their ditches and other open channel waterways are going to be stable or not. So here's the process, and again, the abbreviated information on this is in HDS4. The more detailed write-up on this is the entire HEC 15 document, the design of flexible channels, or flexible linings for channels. And I would refer you to HEC 15 for the most comprehensive coverage. Here's the basic procedure though. We calculate our design discharge. More often than not, that's from the rational method for your ditches. You lay out your preliminary channel, and when you lay out your channel, its shape, slope, maybe even an estimated lining, type things like that. You have to estimate then the flow depth in your channel, and if you're doing this by hand, that's what you're doing. You're estimating the flow depth, because to solve Manning's equation, given the flow, over here you have area over wetted perimeter raised to the 2/3, and as you start plugging in the geometry of your channel for the area in the wetted perimeter, it becomes very convoluted. So it's very hard to calculate your depth directly from Manning's equation. It becomes a trial and success iteration. We like to speak positively, so we say trial and success now, not trial and error. Trial and success. It becomes kind of tedious, but if you're doing this by hand, you estimate the channel depth, you estimate your end value, given relative roughness that we just talked about. You calculate your hydraulic radius, and then you calculate your initial guess at Q. You then compare your initial guess at Q to the actual design discharge, and if it's pretty close, what they say is within 5%, then you've done a good job, and then you use those parameters from Manning's equation then to look at shear stress. If you're not within 5%, your guesstimate versus the actual design discharge, then you have to iterate again and again and again. And both HDS4 and HEC 15 will give you a procedure for re-estimating in your second iteration a new water depth so that you close in more quickly on your estimated Q versus the actual Q. So big picture again, this is getting into the minutia, but just keep your eye on the prize. The big concept is for looking to see if your channel and your selected channel lining are stable, you're just comparing shear stress. The permissible shear stress of your channel material or your channel lining versus what the water is applying to it. Okay? We'll come back and talk about that in a second. All right. So determine the maximum applied shear stress. So what's applying the shear stress? It's the flow. The flow is applying the shear stress. And then you compare the applied shear stress to what your channel material can actually resist. And so this is common sense, pretty easy concept. If the applied shear stress from your flow exceeds the permissible shear stress of your material, what might you expect to happen?
Erosion.
It starts breaking apart, your channel lining gets ripped out, maybe you have erosion, some scour issues going on, and you don't have a successful design. If the applied shear stress imparted by your design flow is less than what can be resisted or permissible, so the applied is less than the permissible, then you're probably good to go, right? All right, so again, this is all written up in HEC 15. You can decide to introduce a safety factor. The default is just one. So this is just saying, is my permissible shear stress greater than or equal to what's applied? And if so, then I'm good to go. If I want to add in a safety factor, that could vary from 1 or no safety factor to maybe 1.5, say. You can add that in there, and then you still do a comparison of, is my permissible greater than my safety factor times the applied shear stress. And if it is, you have a stable channel, congratulations. You know, it's always happy hour somewhere in the world, treat yourself. If no, stay there and do another iteration, tweak your design, make sure that you get to the yes answer. So shear stress. You will see equations for 2 different types of shear stress. Applied shear stress. We are looking for the maximum shear stress. So here's just a diagram showing where the maximum shear stress occurs, and that's going to be on the channel bottom. And it's still fairly large right here in the haunch area here, in the haunch area here. And the shear stress decreases as you approach the water surface, and then eventually at the water surface is 0. And just think about this. If you're down at the river bottom and this flood flow comes along and you have water pushing over you, you're going to experience a lot of shear, right? If you're up here at the top of the bank and the water's barely touching you, you're hardly going to notice anything. So the maximum shear in channel occurs on the bottom. And so when we're looking at the applied shear stress, we're looking for this equation here. The applied shear stress equation is the specific weight of water, which is gamma, and the specific weight of water is typically taken as 62.4 pounds per cubic foot. Is that always correct? No. Because it varies with what? It varies with temperature. Things that we typically don't consider. It would vary with the specific weight of your fluid. What if it is carrying a lot of sediment? What's its specific weight then?
Higher.
Probably a lot higher, which would give you a much higher shear stress. We're not going to worry about that in our ditches. Not going to worry about it. So shear stress is specific weight of water times the maximum depth, and that's that D. And S is, what slope is it? Whenever you see S again in the hydraulics equation, it's always the energy slope. However, we're using Manning's equation for our ditch analysis under steady uniform flow conditions. Energy slope equals channel slope. Okay. So for our ditches, we're just going to say this is the channel slope. That's the maximum, that's the value that we want to look at to do a comparison. You'll also see this equation for average boundary shear stress, and it's still gamma and S in there, which is specific weight of water, channel slope. Now you see the hydraulic radius. So we can actually use the hydraulic radius, but again, that's the average boundary shear stress. We want to make sure that we design for the worst case condition, which is the maximum shear. And so we're actually going to use the depth of the flow and not the hydraulic radius. All right, permissible shear. There's a wealth of information on permissible shear stresses. Are you in non-cohesive soil? Are you in a cohesive soil? Are you dealing with vegetation? Are you dealing with cobbles and riprap? I mean, depending on what material type is lining your ditch, there will be a way to estimate or calculate the permissible shear stress. And again, that's getting down into the minutia. You don't have to remember it all. You just have to know that the permissible shear for riprap and cobbles and gravels is calculated in a different way than vegetation is calculated in a different way than your road erosion control products, and that's different than clay material. And so whenever you get down into the nitty-gritty details, your reference is HEC 15. So here's some examples. Here's a permissible shear for riprap and gravel. This F star is called a Shell's parameter, and that's something that you just look up. You don't have to memorize it or know it off the top of your head. The specific weight of your material, your riprap or your gravel, minus the specific weight of water, just then multiplied by your default. Okay, so pretty straightforward and easy to do for riprap and gravels. Here's some more typical values, and again, this is just to give you an idea. Your non-cohesive soils, gravel, mulch, rock, riprap, the column over on the far right, pounds per square foot. So shear is kind of like a pressure force, pounds per square foot. So these are the units that we typically look for. That will give you an idea of what the various ranges are. So your non-cohesive soil cannot resist very much shear stress. Your rock riprap, it's heavier, can resist a much higher applied shear stress. So that's just to give you an idea of the variation that you make. Cohesive soils get a little bit tricky. In HEC 15, you will be provided with a pretty elaborate equation for calculating the permissible shear stress of clay, cohesive type materials. You know, some of the key parameter that you'll be interested in is the plasticity index, which comes out from your geotechnical testing. But this just gives you an idea of the ranges in shear for different types of soils. You don't have to memorize the equations. Again, if you know that you're dealing with a roadside ditch and you want to see, and if it's in a clay type material, if you want to see that stable, you just need to know that you can then go to HEC 15 and calculate or estimate the permissible shear for that clay material given this elaborate procedure. Other considerations, this is kind of neat, and it's kind of like what Veronica mentioned this morning of, pretend you're a drop of water. We do actually try to visualize a lot as hydraulic engineers. Does this make sense? What's the water going to do in this situation? Which direction is it going to go? Well, the same thing happens in stable channel design. We know that as flow is approaching in this direction, it has to go around a bend from the what equation or principle? Momentum. We know that water, just like people, don't handle 90-degree turns very well, right? So as it comes around here, it's going to brush against this side here, and it's going to be pointed in this direction. And then you're going to have an applied force coming from this bank, pushing the water to go this direction. So we know that going around this bend, the highest shear zones are about right here, and then right here on the outside of the bend. Just from actual measurements that we've done, but you can also visualize this. So you're probably not having a lot of bends in your ditch lines, but if you were doing some work in a stream or a river or whatnot, you would have to consider that you have a higher applied shear at certain points through your curve, and you need to account for that with your protection or your channel lining, whatever you're using. So that's just an awareness, and HEC 15 gives us a procedure to calculate the additional shear stress that's being applied to the banks at certain locations, and it's based on the radius of curvature and then the top width of the flow. And it provides us with a way to calculate an adjustment to account for that higher shear. We also know that as water goes around bends, and this comes out when we start talking about modeling a bit on Thursday morning, the water surface is never flat. HEC-RAS 1D tells us that it calculates a flat water surface. The water surface is never flat. And as it goes around the bend, we have super elevation when we go around bends in our cars, right? Geometric designers lay those out, you lay those out. Water actually does some super elevation as it goes around bends. So on the outside of the bend, the water level will be higher than on the inside of the bend. And so we need to make sure we account for this additional water surface on the outside of our bend if we're using some sort of protection. And there's a way to do that, and that's also in HEC 15. All right, so HEC 15 will also talk about if you're trying to put riprap and gaving and stuff on these steeper side slopes, or if you're designing flexible linings for these higher longitudinal slopes, some different considerations and design techniques. So the moral of the story is, with designing channel linings and flexible channel linings, you need to kind of have an idea of what you want to try, and then knowing that whatever specific material you're looking at, there's a special way to calculate the roughness of that material that you then plug into Manning's equation, that you then use to calculate the flow depth, which you then use to calculate the applied shear stress. And then for that particular material, it will have an innate ability to resist a certain amount of shear stress. And then you just compare the applied shear stress to what that material can resist, and you want to make sure that the applied shear stress is less than the permissible, or what it can actually handle. So the big picture concept is pretty straightforward. In all the minutia, whenever you get to a point where you're trying these things out, you look for the minutia in the equations and the charts in HEC 15 or another resource that you may have at your disposal. You don't have to memorize it. You don't have to know it off the top of your heads. If someone asks you about it, you say, here's the general idea, but the minutia is in this document. Let's go take a look. Okay. Don't clutter up your hard drive, right? I'm always trying to keep my mind free so I can think about cool stuff and not get it all cluttered with numbers and facts and figures. So that's a general overview, but we're going to put this into practice by reviewing an example. So I picked one of the more complex examples just to reinforce the idea that the basic concepts are straightforward. The minutia gets a bit tedious and you have to look up a lot of different numbers, but that's all it is looking up the numbers. You need to understand and be able to master the big picture ideas. So with that, let's take a look at this example. So if you turn to the back of this lesson. Oh, actually, I was going to give you another metaphor, and that's why I had my cat picture. This would have been appropriate about 10 minutes ago, but I can go through it again just to tell you what I was going to say. And then if you want to use it when you're doing your internal training, you can use it or some other similar idea. All right, so I may need some assistance again. Could you, maybe it's just the key that I need to press. If you could, this time I'm going to pay attention.
Just the Windows key.
Thanks, good. All right, so this is McFly. Or when he pees in my slippers, I call him McFluff the crime cat. Kind of like from McGruff the crime dog. You remember those commercials? So I adopted McFly when he was about 3 months old. He was homeless behind my townhouse, and he was probably about that big. So this is 6 years later, and now he's this big and weighs about 13, 14 pounds. So cats, they like to seek out the warm, cozy places in the house, someplace where they feel safe. So of course, if you're not a cat person, and I understand that, maybe you're a dog person, or I think ferrets were a thing back in the day. I even knew people that had pet rats. Whatever your furry suburby friend is, just picture that furry suburby. You're cuddling up on your blanket at night on your bed, and the furry suburby jumps up on the bed and cuddles up there. And where do they like to cuddle up? Right against your legs, and usually right in the middle of the bed. Okay, so you're kind of like formed into a pretzel, and it's very uncomfortable. So about 2 hours into sleeping, I wake up and like McFly's plop right in the center, and he's sprawled out. He expands to about 4 times his normal size. And it's just like I'm so uncomfortable. And so I start doing what? I kind of like start off by giving him a little nudge with my leg. So I'm applying kind of like a shear stress, right? And he goes like this. Nothing. It's kind of like dead weight. It's kind of like a black hole. All the blankets are like pulled into his middle. And nothing can escape. So I give him a little bit harder push, and maybe I push him with my hand. I'm applying more shear stress. But he has the ability, due to his weight and his connection with the material underneath him, to resist a certain amount of shear stress, or he has a permissible. And until I exceed that permissible, he's going to be parked right there in the middle of my bed, and I'm not going to get any sleep. So eventually it gets to a point where I have to really apply so much shear stress, and it makes me feel bad. But sometimes you just got to get a good night's rest. I apply so much shear stress that he eventually rolls and moves away. So that's exactly what is going on in your ditches and your rivers and your streams and whatnot, is I'm the water and I'm pushing. Sometimes if I'm not pushing hard enough, what I'm pushing against is able to resist. When that flood comes along and when I really give them a shove, that's when we come to the test. Am I able to shove McFly out of the way? Is the water able to shove those rocks and your riprap and your erosion control matting and your vegetation out of the way and erode that channel and do what it wants to do? To get back to a resting position, because that's what water does. Water's lazy. It wants to get rid of all of its excess energy and get back to that subcritical tranquil flow. Water does that naturally. Okay. So that was my McFly.